Okay, welcome back to our second set of notes for chapter 14. We're going to try to just cover a bit of ground and just wrap this whole chapter up if we can. So we left off with our rules for writing equilibrium constant expressions. We've had some chance to practice that in class, and hopefully you're starting to feel pretty comfortable with them. So now we're going to look at kinetics and chemical equilibrium and kind of how they're related. So here we've got a just generic reaction, A plus 2B yields AB2. This Kf is the constant of the forward reaction, and Kr is the constant of the reverse reaction. And if we're in equilibrium, these are probably pretty close to the same. So here's our rate law. Then our rate is equal to Kab squared. This is the rate of the forward reaction is equal to the constant of the forward reaction. And then we can say the same thing for the reverse. The rate of the reverse reaction is K of the reverse reaction multiplied by AB2, of course, because if it were the reverse reaction, then this would be our reactant, so our rate would depend on them. So there's some differences there, but hopefully that makes sense given what we covered last chapter with rate laws. And so we can say we're at equilibrium if the rate of our forward reaction is equal to the rate of our reverse reaction. And so then substituting these two formulas in, we can say that at equilibrium our constant of AB squared is equal to our constant reverse of AB2. And so then we can say that our K of our forward reaction divided by K of our reverse reaction is equal to our equilibrium constant, which is AB2 over AB squared, which is what you've been writing kind of this whole chapter to this point. So really we're just proving that these two are very much so related to each other. So this is kind of a difficult concept at first glance. It's called the reaction quotient. We calculate this reaction quotient by substituting initial concentrations of reactants and products into our equilibrium constant. So we just solve for equilibrium constant and then put in our molarities and look at our numbers. So if our reaction quotient is much greater than our Kc, I don't like this picture. This picture does not show that. I don't know why they put that there. Let's try this. Here we go. This is a little better. Okay, so if our Q sub C, our reaction quotient, is greater than our Kc, here we go, then the system proceeds from right to left to reach equilibrium. If our reaction quotient, Qc, is equal to Kc, our equilibrium expression, our equilibrium constant, then we're at equilibrium. And if Qc is less than Kc, we proceed from left to right to make more products. And so we can calculate our reaction quotient, and basically it'll give us a number. And if that number is less than the equilibrium constant they give us in the problem, we need to make more products. If that number is greater than the equilibrium constant in the expression, we need to make more reactants. It tells us if we haven't yet reached equilibrium, or if it's too big that we've overshot equilibrium and need to make more reactants. So calculating equilibrium concentrations. Express the equilibrium concentrations of all the species in terms of initial concentrations and a single unknown. It just so happens that the problems they start you with in your book are pretty manageable. The problem that they do in this set of notes is pretty tough, so don't become too immediately discouraged if we go through this. And if you have great math skills, then you might just be encouraged by this. But I still find this pretty uncomfortable, so we'll go through it at any rate. So we express our change. We write an equilibrium constant in terms of the concentrations, and then we try to solve for x. Once we solve for x, then we calculate the equilibrium concentrations for all the species. So just like everything we've done in chemistry, talking about it doesn't get us very far, but practicing it does. So let's jump straight to that. At 1280 C, so give us a temperature, an equilibrium constant for this reaction is 1.1 times 10 to the negative 3. If the initial concentrations of diatomic bromine is 0.063 molar, and bromine is 0.012 molar, calculate the concentrations of these species at equilibrium. So we don't know if they're at equilibrium yet. We're assuming they're not. So to get to equilibrium, we have to figure out what's the concentration of diatomic bromine and what's the concentration of bromine when they are truly at equilibrium. So the way you do this is you set up ICE, initial change, and then equilibrium. So we're going to say X in our little formula we're going to set up is going to be the change in concentration of bromine. And so here's our equation again. So our initial concentrations are 0.063 for bromine and 0.012 for our product bromine. Now our change is we are losing 1 mole of bromine on the reactant side, so we're going to say that's minus X. And here we're gaining 2 moles of bromine, so the change there would be a plus 2X. And so then at equilibrium, of course, it would be our initial minus our X, and for our products, it would be our initial plus 2X. So that's how we would solve something like that. So that's ICE, initial change, equilibrium. That's how you set that up. So do remember that. So now we set up the formulas we've been writing this whole chapter, which is equilibrium constant is equal to our bromine squared, from that 2 as the coefficient, divided by our concentration of bromine. And because we're going to try to solve for this at equilibrium, our concentration of bromine squared isn't 0.063, it's actually 0.63 minus X. So we plug this with the change into here, and this with the change into our denominator. And we solve for that. And so we say, okay, our Kc at equilibrium should be this squared divided by this, and the problem told me that our Kc was 1.1 times 10 to the negative 3. So I put that equilibrium constant in here, which I could have put here as well, it doesn't really matter. And then we solve for X. Now unfortunately they started us one with X being squared, and we're going to end up using the quadratic equation, and things are just going to go crazy. For the math nerds in the house, that won't be a huge hurdle. That is a bit of a hurdle for me, but we will get there. So now we solve for X. So we say, okay, we've got this equal to 1.1. We go ahead and square this, which I think could totally be wrong here. I think it might be FOIL, like first, outside, inside, last. I mean, let me know if that's even a thing in math. I think it is. And then you would divide it by 0.063 minus X, and you would get this, which is our squared. And we can combine some terms here to try to get it simplified. So we can combine all our squareds and just our X, which is this guy over here, puts us at 491. This stays the same, set that equal to 0. And so now we've got an X squared, an X, and something without an X, and those will become our A, our B, and our C respectively. This is the general formula for what we've accomplished up here. And to solve for that, you use the quadratic equation. Oh my. X is equal to negative B plus or minus the square root of B squared minus 4AC over 2A. Easy as pie. And you solve for X at 0.0105, a negative. Wonderful. So now that we have X, we're still not done. If it's a plus, it's this. If it's a minus, it's this. So they can be a little different. So we have 2 X's now. And we get to solve for equilibrium because we go back to our initial ICE chart and we say, well, we have to subtract X for bromine, and we have to add 2X for our other bromine. So at equilibrium, our bromine concentration here is our 0.012 plus 2X, and that would give us 0.009 molar using that first X, or 0.0844 using the second X. So we use the second X. And then here our BR2 is 0.062, which I think maybe should be 63, but not a big deal, minus X, and so that would give us 0.648 molar. So hopefully most of the problems will be easier than that in your book. Like I said, that kind of takes you through a progression of a little simpler things. They don't just jump straight to quadratic equation. But now we're going to switch gears a little bit to Le Chatelier's principle. And this is really quite a bit simpler conceptually. So this is the idea that if an external stress is applied to a system that's already at equilibrium, the system adjusts in such a way that the stress is partially offset and the system reaches a new equilibrium. So changes in concentration, that'll shift equilibrium. You can shift left or right. If this is at equilibrium right now, and I increase the amount of hydrogen concentration to relieve that stress, the equilibrium will shift to the right. We'll make more ammonia. If I increase the ammonia concentration to relieve that stress, the equilibrium will shift left. Stuff like that. So Le Chatelier's isn't too bad. If we add NH3, equilibrium shifts to the left to offset the stress of having more ammonia. And so here's Le Chatelier's principle in a graph. So we look at changes in concentration. If we add the concentration of the products will shift our equilibrium to the left. If we remove some of our products, then we have less on the right than we had before. So to relieve that stress, you can kind of think of it as allowing more space for reactants to become products. We'll still shift this equilibrium to the right if we remove our products. So Le Chatelier is pretty easy. Oh, sorry. If we increase the concentration of our reactants, of course, and then there's a lot of pressure over here to relieve that stress, we're going to progress to the right. And that's Le Chatelier's. Very simple, I hope. And if we remove our reactants, then of course we'd be shifting to the left, because there's more space on the left now. So Le Chatelier's principle is really not too bad. If we change volume and pressure, we're going to want to look at the moles of gas. So here we've got, if we're increasing the pressure, we've got 2 moles of gas at reactants and 1 mole of gas in the products. And so you can kind of think of it as 2 moles of gas takes a lot more space than 1 mole of gas. So if I increase the pressure, it'd be more favorable for me to be 1 mole of gas. I'm not going to take as much space that way. So you'd actually shift that equilibrium to the right. If we decrease the pressure, then it's the exact opposite. You've got all the room in the world, be as many moles of gas as you want. We'd shift it to the left. If we increase the volume, we'll go to the side with the most moles of gas, because if you have a bigger space, you can have a lot of moles of gas. If you decrease the volume, you don't want a lot of moles of gas. You'll go to the fewest moles, which would be our right side. And that's kind of how volume and pressure can affect Le Chatelier's principle. But do remember, it's just moles of gas. If you're looking at a longer, more complicated equation, don't count solids and liquids moles. That'll just mess you up. It's gases that respond to pressure change, not solids or liquids. So if we change in temperature for Le Chatelier's principle, if we increase that temperature, if it's an exothermic reaction, we'll actually decrease that equilibrium constant. Whereas if it's an endothermic reaction, increasing the temperature is a good thing. We'll increase that equilibrium constant. If we decrease the temperature, then it's the exact opposite. For an exothermic reaction, decreasing the temperature increases the reaction, increases equilibrium constant. And for an endothermic reaction, it would decrease that K, because if you're decreasing the temperature and it's endothermic, of course endothermic wants to release heat. If it's very cold, then it's going to be a little more difficult to do that, and so we're going to decrease its constant. And so here's our example. N2O4 going to 2NO2 is a delta H of positive 58, so since it's positive, that means it is endothermic. And here's our example of these two. If they're colder, we're shifting to the left, N2O4. If they are warmer, we shift to our right, and we get more NO2. And we can see that based on their colors. So that's Le Chatelier's principle. If you add a catalyst, it doesn't change our equilibrium constant at all. It makes the reaction happen faster, but that does not favor more reactants or more products or anything like that. It just makes it quicker. So it does not shift the position of an equilibrium. It just makes the system reach equilibrium faster. And so here's kind of your graph that you've seen before, really. Activation energy is very high. Without a catalyst, activation energy is much lower with a catalyst, and the result's really the same, that you're getting reactants to products. This is just going to happen quicker because there's a lot less activation energy with a catalyst. So the catalyst lowers the activation energy for both the forward and reverse reactions, so it doesn't affect our equilibrium constant. Catalysts don't change the equilibrium constant, and they don't shift the equilibrium. Some applied chemistry for equilibrium. This is life at high altitudes and hemoglobin production. Here you have some mountain climbers. They're up very, very high. Hemoglobin and oxygen is a reaction in equilibrium because hemoglobin can bind to oxygen to make oxyhemoglobin, which is what's carrying oxygen through your blood. But oxyhemoglobin can also become hemoglobin and oxygen and let go of that oxygen, and so our equilibrium is equal to the oxyhemoglobin divided by the hemoglobin and the oxygen. And the reason it's so important for mountain climbers, and the reason they have to either take a long time to acclimate to the altitude, carry oxygen with them, things like that, is there's a lot less atmospheric pressure at those high altitudes. So when there's a lot less pressure on that oxygen, it's a little less likely to form this bond with hemoglobin. It's just not as concentrated in the atmosphere the higher up you go. And so there's just not as much pressure up there. There's not as much oxygen per liter of air. It's a little more dispersed, and so it's important for these guys to take time to acclimate to the low oxygen levels, whereas the folks who have lived there their whole lives, they actually have a ton of red blood cells, a little more than us, a little more concentrated as a way to kind of adapt to that environment. And so altitude sickness is a real thing. You got to take your time up there. Here's the Haber process for making ammonia, and it's basically, the reason it's so successful is because it's manipulating Le Chatelier's principle. Here we take hydrogen and nitrogen, and you can see there's 1 mole, 4 moles of gas to 2 moles of gas. So if you want to make a bunch of ammonia, add pressure. You add pressure, it's going to go from 4 moles to 2 moles. So they add pressure through a compressor, they run it through a catalyst, they make a bunch of ammonia. Now, if you want to keep that reaction going, take the ammonia away. If you take the ammonia away, there's more room on the product side for reactants to form more products. So you pull that ammonia off, you take that hydrogen and nitrogen back to the compressor, they make more ammonia, you pull the ammonia off, recycle nitrogen and hydrogen back to a compressor, around and around and around it goes, and you can make a lot of ammonia that way. So it's kind of a cool application of Le Chatelier's principle. You can get a lot of ammonia for fertilizers and bombs and stuff, that kind of stuff, I think was the reason they were working on it in the first place, but still, it's kind of a neat process. So, in summary, things that will change your equilibrium and change your equilibrium constant. If you change your concentration, that'll shift your equilibrium, but it shouldn't change your constant. If you change your pressure, that'll shift your equilibrium if it's gases, but it shouldn't change your equilibrium constant. If you change the volume, that'll shift equilibrium if it's gases, and it won't change your equilibrium constant. Temperature will shift your equilibrium if you're exothermic or endothermic, and it will change your equilibrium constant. A catalyst will not change your equilibrium, and it will not change your equilibrium constant. Just makes it quicker. And with that, guys, I think we are pretty much wrapped.